Hello everyone. In this video I'm going to go over the Math-108 homework on binomial distributions. So at the top here I've placed some information in the box for you. The probability of observing R successes in n trials of a binomial experiment is given here by this formula. And then down here I explain what all the different letters stand for. So n is the number of trials, R the number of successes, n minus R then is the number of failures. P is the probability of success on a single trial, and 1 minus P then is the probability of failure on a single trial. So let's look at some binomial experiments. The first one is drawing 4 cards from the standard deck with replacement. So each individual trial is drawing 1 card, and then success is getting a heart, and failure is not getting a heart. So first we need to write down the values that we know so far. So we can figure out what n is. That's the number of trials. So that is going to be 4, because we're drawing 4 cards. And then, oops, what did I do there? Okay. And then next, P, the probability of success on a single trial, is that is going to be the probability of drawing a heart from the standard deck of cards. So this is 13 out of 52, or 1/4. Or you could write it as 0.25 if you want. Either of those ways is fine. And then 1 minus P, probability of failure. Prob, not prof. Ooh, being the prof of failure would be strange. Okay, so 1 minus P is then 3/4, or you can write it as 0.75 if you want. Okay, we're going to actually be plugging these answers into a calculator or the Google search bar. So I'll write them in decimal form, because that's easier for the calculator. Okay, so now we have a table down here, and we're going to fill this in with the probability for each possible number of successes using the formula. So the only thing we don't have is the value of R, and that is going to be what's going to change in each row of the formula here. So for the probability, we're going to be using this formula from up here. So I'm actually just going to paste this down here, and I guess I'll just go ahead and put it in. Actually, let me fill in the parts that are going to be the same for all of them first. So n is going to be the same. That'll be 4 for all of these. P, which is 0.25, that's going to stay the same for all of these. Probability of failure, 0.75, that'll be the same. And then n minus R, n is 4, so this 4 minus R, this is going to be the number of failures on each trial. Okay, so now I'm going to copy paste this into each row here. Boop, boop, boop. It's more fun if you make sound effects. Okay, so the number of successes in the first row is 0, 1, 2, 3, 4, and then I've got to change these exponents as well, and the other exponent. So if we have 0 successes, that's 4 failures. 1 success is 3 failures, or 4 minus 1 is 3. Okay, I'll just pause it and do the rest of these. Okay, so I've got them all filled in now, and for days when you don't have a calculator, I might give you permission to just leave it unsimplified like this, like on a quiz or something, or a test. But for this particular homework, I'd like you to find an actual approximate calculator answer, because I want to show you something like somewhat interesting about what the expected value over here for the number of successes actually ends up being. So I'm going to go to the Google search bar, and I'll show you how to enter these and get an actual approximate answer. Okay, so the way that you want to type these in is you want to have the parentheses for choose 0, the choosing part like this in parentheses. And that's just so that you can multiply that whole number by the next part. And then you're going to have the probability of success, and then raise that using the caret key, which is shift 6, to the number of successes. So the first one is 0. And then do another multiplication, and the probability of failure, 0.75. And then raise that with shift 6 again to the number of failures. And you don't need any other parentheses. The order of operations here is correct. The exponents will be done before the multiplication. So you can go ahead and enter that. And I momentarily got distracted by this little pi symbol here. It is actually Pi Day tomorrow, so like the day is 3/13. So this is like a little Google Doodle thing. It's not part of the answer. That was very distracting. Thanks a lot, Google. Okay, so I'm going to just take this answer and paste it back into my sheet over here. Okay, So the approximately 31% probability that you actually get no hearts. Okay, and then I'm going to go ahead and also work out the fourth column here because I'm going to have to multiply that by the first column over here. So I'm multiplying these two cells together to get this last one. And I'd rather do that like while I still have it typed into Google in the bar up here. So this one's 0, but for the rest of them, it'll be easier to do it this way. Okay, so now I'm going to enter the next one. So this changes to 4 choose 1, 0.25 to the 1, 0.75 to the 3. Okay, so I'm getting 0.421875. I'll put this back over here. Okay, and then I'm going to go ahead and, well, multiplying it by 1 doesn't do anything, so I guess this will be the same in the last column here. Okay, and then the next one I'm going to change to 2 successes, so it'll be 4 choose 2, 0.25 to the 2, 0.75 to the 2. Okay, copy this, and then for the last column now, I do actually have to multiply that by 2. So I'm going to go ahead and put that into the formula here. I'll just multiply it by 2 at the end there. So that's 0.421875. Wait, wasn't that the last answer? Oh yeah, it just happens to be the same as the as this answer up here. I think it's just a coincidence. Okay, and I'm just going to go ahead and do the rest of them like that, so I'll just pause the video so it doesn't bore you guys. Okay, so I went ahead and finished all of them, and one thing that's interesting here is you might notice that the first probability of getting no hearts is kind of high, which actually should make sense because we're only drawing 4 cards, so it's, yeah, I mean, it's like possible that you don't get any hearts. The highest probability corresponds to the proportion of hearts that are in the deck. So 1/4 of the cards are hearts, and this is saying the highest probability is that you get 1 out of these 4 cards that you draw is a heart. That makes sense to me. And then the probabilities go down from there on the other side, and getting all 4 hearts is like super unlikely, which is why that's like a winning hand at poker when you get a flush of, you know, all the same suit. Okay, so over here I multiplied these by the number of successes from this column, and now I just need to add them up, and you can just use a regular calculator for this. So what you'll see if you do this is that you get exactly 1. And that might seem really weird, but actually, if you think about it, it's the same thing I was talking about up here of why this is the most likely outcome of getting 1 heart. So it's not only the most likely outcome, it's the expected outcome. If you were to draw 4 cards from the deck with a replacement and you did it over and over and over and over and over again, on average you would see 1 heart would be the average number of hearts that you would get by doing that experiment, which makes sense because it's 1/4 of the cards in the deck and you're drawing 4 cards. Okay, so this is like something you probably could have predicted even without actually doing these calculations. All right, now let's do something biology related. A certain variety of tissue has the property that its cells take 24 hours to divide. During 1 hour of observation in the lab, each cell has a 4% chance of dividing, independent of what any other cell is doing. So this is like a somewhat realistic thing. Like this actually is how bacterial growth and cell growth and stuff works. I don't know that there's strict independence of cells because they have to like share resources and stuff, but it's not completely unrealistic either. All right, so for the purposes of this problem, we're going to assume that the cells are independent of each other. Okay, so we can interpret observing the cells for 1 hour as a binomial experiment with 1 trial for each cell, where success means that the cell divided and failure means that the cell did not divide. Suppose we observe 100 cells for 1 hour. So first, if we're going to treat this as a binomial experiment, we've already been told what the trials are and what success and failure are. Now we need to figure out what these 3 quantities are that we use in the formula. So n is the number of trials. So that is going to be, it's 1 trial for each cell, and we're observing 100 cells for 1 hour. So this is 100 trials. It's like 1 trial per cell. And then P is going to be the probability of success. So let's see, that was given somewhere, yeah, a 4% chance of dividing. So this is 0.04. And then 1 minus P is the opposite probability, so 0.96. Oops, 1 minus P. Okay, so that's the probability of failure. All right, so now it says for number 6 through 8, so for these, we need to first find the R and the N minus R values, that's number of successes and number of failures, and then use the binomial probability formula. You can leave your answer unsimplified, so no calculator or Google bar needed. And I swear, Microsoft Word, unsimplified really is a word. I keep trying to tell it this. Okay, so what is the probability that none of the cells divide? So first we need to figure out the R and the N minus R values. So N we know is 100, R is the number of successes. So R, number of successes. That is going to be, if none of the cells divide, then it's 0. Okay, and then N minus R is, N minus R is number of failures. So that is going to be, if none of them succeed, then they all fail, so that's 100. And I'm going to go ahead and just do that for these other two as well. So R here, if 4 cells divide, R is 4, and then N minus R is 96. And if 10 cells divide, that's what R is, and then N minus R is 90. Okay, so that we need that stuff to plug into the formula. So now I'm going to come and put the formula in here and figure out the probability for each of these R values. So I'll just copy it from up here. I don't think this formula is like horrible to memorize because it kind of makes sense like why it is what it is, and it has some like symmetry to it, but I usually don't ask students to memorize this because it's too many pieces. It's not the worst formula I've ever seen, but it's not a great one either. Okay, so this is 0.04. That's the probability of success, and this number of successes for this one is for none of them to divide, so 0. So they're all going to fail, so all the exponents go into here, all 100. So basically, probability of failing 100 times in a row right there. And I'm just going to copy paste this for the other. Oops. Microsoft Word, you're so confusing with all your line breaks and your carriage returns and okay. Anyway, so I'm going to change this number to 4. This one changes to 4. And this one changes to 96. And then down here, this is going to be 10. And this will be 10. And this will be 90. So you notice that your two exponents always divide up to what your number, or sorry, your two exponents always add up to what your number of trials was. And then your two bases that have the exponents always add up to 1. So it has this kind of like symmetry to it. Okay, and then we didn't have to plug that in, so I'll just leave it like that. All right, last set of problems here. M&Ms. According to the manufacturer, 20% of peanut M&Ms are blue. I don't remember if this is true or not, or if I actually looked this up when I wrote this. This means that if we randomly select a single peanut M&M, it has a 20% probability of being blue, independent of any other peanut M&M. Suppose we have a fun-size bag containing 10 peanut M&Ms. If we interpret this as a binomial experiment, what are the trials? Okay, so what is the thing that we're going to do over and over again and like check for whether something happened or not? In this case, actually, you kind of need to like read ahead a little bit to see what are we trying to find the probability of. We're trying to find the probability that the bag contains different numbers of blue peanut M&Ms. So we can interpret that finding a blue peanut M&M must be a success. So then the trials must be like looking at the M&Ms. Okay, so looking at one M&M. Now you might be wondering, is this actually independent? If the probability here came from the bag itself, then looking at the M&Ms separately, they would not have independent probabilities of success because the success of one would change. Like once you knew whether one was blue, that would change the probability that the others were blue. Because like if you look at all of the blue ones, then you're done with them and it goes to 0. But this probability, the 20%, this is coming from the manufacturer. So like at the moment of creation of every peanut M&M, it had a 20% chance of being blue independently of the other ones. That's the way we're thinking about it. So in that sense, each trial of looking at one M&M is independent. Okay, so anyway, yeah, so looking at one M&M is a trial, and then we're going to call success as staying the blue one. It's blue, and then failure is not blue. Okay, so now for the number of trials, N is, we're going to look at every peanut in the bag. because this says what is the probability that the bag contains, so we must be looking at all of them. So n is going to be 10, probability of success is going to be 20% or 0.2, and that makes probability of failure is 0.8. Okay, so now that we have all of those, for the rest of the problems here, well, actually just for these three, we're going to find our n and our n minus r, sorry, our r and our n minus r values, number of successes and number of failures, and then we're going to plug those into this binomial probability formula, just like we've been doing. And then the last two here, actually, you need a different way of calculating the probability, because this is 2 or less and 3 or more. So we can think about those once we get to them. Okay, so for number 12 here, the number of successes is, we're looking for no blue, so 0. And that makes the number of failures is going to be 10. For the next one, we're looking for 1 for R, and that means the number of failures is going to be 9. And then the next one, R equals 2, and n minus R equals 8. So 2 successes and 8 failures. And now we're going to put the formula in from up here. Okay, so number of trials is 10. Number of successes we're looking for this question, it's 0. Probability of success, 20%. Number of successes, 0. Probability of failure, 0.8. Number of failures, 10. Right, and I'm just going to copy paste this again for these ones. And for this one, and I'll just change the numbers. So this is going to be 10 choose 1, 1 success, and 9 failures. And then down here, 10 choose 2, 2 successes, and 8 failures. Okay, and we're not plugging these ones in, thankfully. Now, what is the probability that the bag contains 2 or less peanut M&Ms, blue peanut M&Ms? So 2 or less, you have to interpret that as meaning 2 or less means 2 or 1 or 0. And once you realize this is an or event that you're trying to find the probability of, and that these are mutually exclusive ways for the event to happen, you have to have either 2 or 1. You cannot have both. Or 0, you cannot have both. That means you can just add these 3 answers together. Okay, just like you would do if they were in a table, like if they were in this table up here and you wanted to know the probability of getting 2 or fewer hearts, then you would add these 3 together for 2 or fewer. All right, so we're just going to add together those answers. Add together answers for number 12 to 14. So for if you don't have a calculator, I mean, you just have no recourse but to write it all out. That's kind of the only option. It's a bit unwieldy. Okay. And then for the very last question, sometimes students see answers like this and they think it can't be this complicated. I must be wrong about this. No, it can be this complicated. It can be even more complicated. Okay, this level of complication doesn't scare mathematicians at all. If it gets to like more than 1 page, then I might be a little concerned, but even then. Okay, so the last one, what is the probability that the bag contains 3 or more blue peanut M&Ms? So we could figure this out by getting the answers for exactly 3, 4, 5, 6, 7, 8, 10, 9, and 10, and then add those together. That would be too much work though, because all you have to do is realize that 3 or more is the opposite of 2 or less. Okay, so this is the opposite. Oh, why did I go over there? This is the opposite event from 2 or less. So we can do 100% minus the probability from 15, or 1 minus the probability from number 15, right? Like when there's a 30% chance of rain, there's a 70% chance of no rain. It's that kind of thing. So I'm just going to do 1 minus this answer from number 15. 1 minus, and then I'm going to put the whole thing in parentheses. Oops. It doesn't let me paste line breaks, so I have to make sure not to get that very last character. There we go. Okay, so this was the most complicated answer. Well, it was the last question, so you can expect that from me. All right, that's it for this homework, and I will see you in class.